Welcome back to Chem Talks. In this installment, we are going to look at isotopes in more depth. We introduced them last time when we talked about the subatomic particles. Today we're going to talk about, once again, what isotopes are, how they vary, and how they're related to the atomic mass. We're going to start by reviewing a couple terms from last time, and then we'll get more into isotopes themselves. First thing we got to remember is the atomic number. Remember, atomic number refers to the number of protons in an atom. Remember, all atoms of the same element have the same number of protons. The number of protons can't change. It's what is used to identify the elements. It's what we use to organize the periodic table. It goes from atomic number 1 hydrogen all the way on up to some of our newest atoms. And depending on what periodic table you use or what you're looking at, it may be in a slightly different place in the symbols, as we see up above. Generally, it's going to be a whole number. Okay, the second thing we talked about next time is mass number. Mass number refers to the number of protons and neutrons in an atom. For example here, which we talked about, did this one last time, oxygen has 8 protons and 8 neutrons. So we add those together and it has an a mass number of 16. So this isotope would be oxygen 16. We can think of isotopes simply as varieties. Okay. Isotopes, remember, are atoms of the same element with different number of neutrons. The number of neutrons in the nucleus can change without changing the element, but we can't change the number of protons. For example here, oxygen has 3 isotopes, oxygen 16, 17, and 18, depending on whether it has 8 neutrons, 9 neutrons, or 10 neutrons. Here's a list of just some of the isotopes of the first 6 elements. You can see hydrogen, for example, has 3 common isotopes, helium 3, lithium 3, beryllium 2, boron has 3 there, and carbon has a bunch. What's it, about 6 of them? Okay, but not all of them. You can see if we look at percent abundance, which means how frequently we find them, not all the varieties are common. Carbon, for example, only has 2 fairly common varieties. When we talk about isotopes, we generally state, are they stable or unstable? A stable isotope will maintain a constant concentration on Earth over time, meaning it's not going to break down. Versus an unstable isotope. Unstable isotopes are atoms that disintegrate or break down at predictable and measurable rates to form other isotopes. Okay, generally what we say is these are radioactive. Okay, unstable isotopes referred as radioactive because they break down. And what we see is as they break down, they give off nuclear radiation in the form of rapidly moving particles or high energy electromagnetic waves. And that's what we mean by radioactive. They're breaking down, they're giving off these particles. And as they give off these particles by decaying, they change from one atom or one isotope form into another. For example, carbon-14 will break down into carbon-12. Maybe you've heard of this. This is what we use for carbon dating, for telling how old something is. Well, in general, what we see is that the heavier an isotope is compared to its most common form, the easier it's going to break down, or the more unstable it is, and the faster it will decay. And these unstable isotopes continue to decay or to give off radiation until they become stable, until they hit one of the stable forms. Okay, uses for isotope. Well, we already talked about carbon dating, which is telling how old something is. We can also use it for food preservation or medical equipment sterilization. They use cobalt-60 for that. We can also use it in smoke detectors to help detect smoke. We find it in medical uses in something called biological tracing. They can put an isotope, inject an isotope into your body and follow it through your body to see what's going on, see if there's any blocked arteries or veins. We can also see it in explosion detection. If you've ever gone through one of the puffer machines at an airport when you've flown, those use isotopes. The big question, though, that we're going to address today is what's the relationship between atomic mass and isotopes? For example, if the mass number of oxygen is 16 then why does the periodic table say 15.99 as example down here? Here's our atomic number. Here is 15.99. Well, the answer to this is pretty simple. The number shown on the periodic table is not the mass number. It's the atomic mass, or the weight of a single oxygen atom. Okay? Remember, atomic mass is an average of the masses of all variety of oxygen found on Earth. So looking at all the isotopes. Okay? Remember, oxygen has 3 common isotopes. So in order to give a atomic mass for the periodic table, we have to average these three variations together to get our what we call the weighted atomic mass. Okay, remember, atomic mass is the weighted average mass of all the isotopes. So in order to calculate it, we basically need to know 2 pieces of information. First one we need to know is the mass in AMU of each of the isotopes of the atom. So how much does each isotope variety weigh? The second thing we need to know is something called the fractional abundance. And all the fractional abundance is how frequently does it appear in nature. Let's go back and look at some common isotopes here. Okay, you can see here in this column we have our atomic masses. We can calculate those out. Then we have the percent abundance. Okay, well, percent abundance is related to fractional abundance. The difference being the fractional abundance is the decimal form of the percent abundance. So the fractional abundance for hydrogen 1 here, instead of it would be 0.99985. For hydrogen 2, it's 0.00015. All we need to do is move the decimal places 2 places to the left. So let's look at how we set up these problems for figuring out the atomic mass. Okay, to calculate, what you need to do is take the mass times the fractional abundance for each isotope and add each of those together. So let's say we have 3 isotopes, like in oxygen. Okay, with isotope 1 mass times fractional abundance of that. Isotope 2 mass times fractional abundance. Isotope 3 times fractional abundance. And then we add these all together. Okay, and what we get then is the weighted atomic mass. This is the number that appears on the periodic table. So let's try an actual problem together. Look at oxygen again. This comes up from that yellow graphic we had earlier. So what we're going to do is take the mass times the fractional abundance. Remember, the fractional abundance here is just the percentage put in decimal form. And we do this for all 3 of them. Remember, our mass should be in AMU. I should have AMU units in there. Remember, don't have naked numbers. Once we get this down, we add them all together and we get an atomic mass of 15.99937. If we look at most of our periodic tables, say 15.99. Okay. Pretty simple. Here's a practice problem. Copy this practice problem down. Once you get it copied down, pause this video, and then come back once you figure this out, and we'll work through it together. But please do this problem on your own, then come back. Okay, so here is our 2 isotopes, chlorine 35 and chlorine 37. We do it just like we did in the previous one. Take the mass in AMU times the fractional abundance. Once again, I should have AMUs there, but I forgot to type them in, so make sure you have them in yours. Add them together and we get 35.54 AMU, which should be on your periodic table. Easy. Let's make it a little bit harder and try this next problem together. It says, if naturally occurring boron is 80.2% B11 with an AMU of 11.009 and some other form of boron, so there's 2 isotopes that make it up, they want to know what must be the mass of the second isotope in order to account for a 10.811 AMU weighted average mass. So they want to know what's the mass of the second isotope for boron. So let's work through this one together. Okay, first thing, we know the percent of boron 11. We need to figure out what's the percent of the second isotope. Well, we know percentages add up to 100. So do a little subtraction. Take 100 minus 80.2 and you get atomic mass of 19.8. That's the percentage of our second isotope. So now that we know that, we can set up our problem. What we're trying to solve for, our variable, is the mass. So we'll set it up something like this, where here's the mass of B11, here's its percentage. Here's the mass of the second isotope. This is what we're solving for. Here's its percentage, which we figured out from here. And then the mass of boron itself, given up periodic table, is 10.811. That came from our periodic table. Now, if I didn't give you that, you could just look on the periodic table and get this. So what we have to do now is rearrange and solve for x. So first thing I'm going to do is kind of isolate x by itself. Okay, so I just simply take the mass of it minus the mass times the fractional abundance. Then I get x. Now to solve for x, all I have to do is divide by both sides by the same thing, which is 0.1980. Okay, and then do the math. And I come up with 10.01 AMU. That's the mass of the second isotope. Okay, hopefully you're following me. If not, you need to come in and see me get extra help. I have two homework problems for you. What I want you to do is to copy down this one. Once you get this one copied down, go on to the next one and work on it. This one is number one is straightforward. It's just like we did in the previous problem. So copy this down and come back and see me when you get it copied down. Alright, here's number two. Copy this one down. This one's going to be more challenging for you, okay? Because you have two variables that you're dealing with. So here's my hint. Set your percentages up as x and y, and then solve for x. Okay. Hopefully you know what I'm talking about. If not, there's a good chance for you to come in and chat with me in the morning and see what you're doing. So please work out both homework problem number 1 and number 2. Bring them into class complete, and we will check and see how you are doing. Until I see you in class, guys, take care. We'll talk to you later.